In its theoretical state, a project plan is a pristine blueprint. Every variable, from labor output to material costs, is calculated before a shovel hits the dirt. Once ground is broken, the project faces construction entropy. Weather delays, price spikes, and site failures occur. Physical execution shatters the original hypothesis. A baseline establishes the target, but without a method of enforcement, there is no way to detect when a project has drifted away from its original trajectory. Project control is often perceived as behavioral micromanagement or the restriction of employee freedom. In commercial practice, controlling functions as a data-driven engine. It is the systematic process used to align actual site performance with the planned objectives. This diagnostic engine defends the project against the three primary forces of entropy, collectively known as the iron triangle, delivering the work on time, within cost, and to the specified quality. To understand how capital is protected, we must build the mechanics of this engine, map the timing of its interventions, and apply it to each vertex of the triangle. If planning creates the project's baseline, controlling provides the active mechanism required to defend it against the variables of physical execution. Moving from abstract goals to site-level procedures requires a sequential loop. The controlling function is built on 4 fundamental steps. Step 1 is establishing performance standards. Baselines must consist of specific, measurable targets tied to organizational objectives. This ties into management by objectives, or MBO, where specific goals are translated into clear targets so every team member understands the intended outcome. Step 2 requires measuring actual performance through objective data, such as site reports and interim valuations. An interim valuation is a formal assessment of the physical work completed to date, used to authorize internal accounting and process payment applications. Step 3 is comparing that actual performance against the standards. This reveals the mathematical gap between the plan and the current reality. This gap is defined as the variance. Quantifying this deviation allows a manager to pinpoint exact financial leakages or schedule delays within the broader project. Because execution is rarely perfect, managers define an acceptable range of variation. A metric must cross the specific threshold before an intervention is justified. When variance exceeds that range, Step 4 is triggered, taking corrective action. The manager either intervenes to correct the site performance or, if the initial standard was flawed, revises the baseline itself. This continuous 4-step loop allows a commercial manager to diagnose deviations and address the causes of project failure. The diagnostic engine depends on timing. Managerial interventions are categorized based on where they occur in the project's timeline. Feed-forward control is a proactive, preventative measure. It is designed to anticipate and eliminate issues before physical work begins. A common example is vetting a subcontractor's financial health and resource availability prior to contract award, preventing potential downstream insolvency. Concurrent control involves the real-time monitoring of activities. It allows a manager to step in and correct issues as they happen on site. If a batch of concrete fails a slump test, concurrent control involves halting the pour immediately, preventing defective material from curing. Feedback control is the reactive analysis of completed work. While it is the least proactive type of control, it serves as a vital learning mechanism for future efficiency. Final account audits and post-project cost reviews allow managers to use past performance data to improve the accuracy of future baselines. Proactive timing distinguishes a commercial manager who protects the project from one who simply documents its outcome. We can now apply these mechanics to the first vertex of the iron triangle, cost. This line graph maps actual expenditure against a forecasted budget baseline. Financial control involves the continuous tracking of these metrics to ensure the project remains viable. Managers use cost-value reconciliation, or CVR, to formalize this process. The CVR compares the value of work completed against actual costs incurred, identifying financial leakages early. Cost control also includes cash flow forecasting. Construction contractors are typically paid in arrears, meaning they often fund labor and materials before receiving client payment. Mapping project income against expenses ensures the business has the liquidity to pay wages and procure materials without relying on external loans. Without rigorous reconciliation, a project may appear successful on site while suffering significant financial losses in the ledger. The second vertex is time. Schedule drift poses a financial risk because delays inflate indirect overhead costs, such as plant hire and site management. This S-curve graph illustrates earned value management, or EVM. EVM is a quantitative metric that integrates project scope, time, and cost, comparing the baseline budget for scheduled work against the value of work actually completed. EVM acts as a quantitative early warning system. It allows project managers to pinpoint delays and implement recovery plans before the schedule is impacted. Time control also protects against liquidated and ascertained damages, or LADs. LADs are predefined contractual financial deductions levied against a contractor for failing to deliver the project by the agreed completion date. Using EVM to forecast delays allows a manager to proactively accelerate work, avoiding the triggers for these contractual penalties. Rigorous time control serves as a proactive defense of the contractor's capital. The final vertex involves quality and safety. A failure in either category often invalidates the cost and time baselines. Failing a quality inspection creates significant costs. It requires pausing the schedule to tear down non-compliant work and repurchasing materials to rebuild it. Quality is enforced through non-conformance reports, or NCRs. An NCR is a formal metric used to track any deviation from project specifications, ensuring that rework is minimized. Similarly, safety control involves compliance audits and near-miss tracking. A single accident can halt a site, resulting in schedule disruptions and legal claims. A project delivered within its cost and time parameters still fails if it does not meet its specified physical and safety tolerances. Mechanical loops and S-curves look flawless on paper, but they are executed by humans. Using monitoring as a punitive tactic signals a lack of trust to the team, which often leads to resistance and behavioral pushback. Forcing teams to meet rigid standards without accounting for site realities causes psychological stress. Extreme pressure can encourage teams to falsify reporting and site information to hit their required numbers. This falsification compromises the mathematical integrity of the control loop. It feeds corrupted data into the system, obscuring site realities from the manager until the project is in crisis. Over-centralization and rigid controls create a silo effect. This reduces the organization's flexibility to solve unforeseen site problems. To drive performance effectively, a manager must build specific characteristics into the control system. Controls must be objective. Minimizing subjectivity ensures that performance evaluations are fair and free from bias. The system must also be economically viable. The administrative cost of monitoring software and personnel should not outweigh the financial benefits the system provides. Effective control systems are participative. Framing controls as shared, transparent mechanisms allows a team to monitor progress and maintain the project baseline from within.